Continuation of a fraction. So for today's class, we'll start with a triangular prism. Suppose for this prism, we have light coming this way. When light hits the prism at this side, let's put a normal here. This light will not continue along this direction due to refraction. Let's say it's moving from air to the glass. Less dense to a denser medium, it's moved towards the normal. This is the normal. So this light will refract and move towards the normal. We'll have something like this. So this is the incident ray, refracted ray. At this point, let's put another normal here. So this ray will not continue along this path. So from a denser to a less dense medium, from glass to air, it will bend, is it towards or away? Away from normal, then we'll have something like this. So this is what we call the angle of incidence. This is the angle of refraction. And this is the angle of emergence. And when notice if you measure this and this, you see that the angle of emergence is far greater than the angle of incidence. For the ray, this is the initial direction, and this is the final direction. So the angle between the initial direction and the final direction is called the angle of deviation. So D is what? The angle of deviation. Now, the next thing we want to do here is to express the refractive index of this triangular prism in terms of what? Angle of deviation. But to do that, we want to do a small geometry. Let's suppose this is a right angle triangular base prism, meaning all the angles are equal. They are all 60, 60, 60. Let's call it A. That A is called the refractive angle of the prism. If we are to sketch the angle of incidence, or if we are to sketch the angle of deviation against the angle of incidence, suppose here we have the angle of incidence angle of deviation D against angle of incidence I. We notice something. As we increase the angle of incidence, the angle of deviation will decrease. Suppose initially, for this angle of incidence I, the deviation is D. For this value of I here, deviation is D. As I is increasing, deviation will decrease. Angle of deviation will decrease. When I get to about a certain point, the angle of deviation will stop decreasing and it starts increasing. So meaning angle of deviation initially falls as I is increasing. If you continue to increase the value of I, angle of deviation will now start increasing back. So at this point, the angle of deviation is minimum. So this is what we call the what? Angle of what? Minimum deviation. Let's write it as, okay, let's call the angle of deviation big D, capital D in general. Then the angle of minimum deviation, let's call it what? Small d. So whenever our angle of deviation is minimum, the angle of incidence here at that moment equals to what? The emergent angle of emergence. For angle of incidence to be equals to what? Angle of emergence, angle of deviation must be minimum. And in that case, for I and E to be equal, one thing must happen. When we increase this I, the value of I is increasing, E will decrease. At the end of the day, this refracted ray will parallel to this base. So in short, we are going to have something like this. Let's say this is normal. If we increase the angle of incidence, when it gets here, it will not continue along this path. It's going to diffract towards the normal. So it refracts rather. So this incident ray, this is the refracted ray. When it gets here also, it's not going to continue along this path. Let's draw it again. When it gets here, let's put another normal here. It will not continue here. This time around, it will bend away from this normal. So this way will not go to bend away. So at the end we have something like this. This incident ray, refracted ray, emergent ray. Initial direction, final direction. This is the angle of what? Minimum deviation. In that case, angle of incidence I, angle of emergence E will be equal. And this is what? Angle of what? Refraction. This is A. And we can prove by geometry here. We can prove that our refractive index or refractive angle of this prism equals to R plus R. We can show it if you extend this and extend this. This will have equal length. So if this is R, this will be R. If this is A, we can show that this is also A. This will be A. Similar to side quadrilateral. So this is also R. In this case, this A is like exterior angle to this triangle. So A equals to R plus R. In this case, A equals to 2R. Then we can get the value of R. R to be equals to A over 2 in this case. This only occurs when the angle of deviation is minimum. When the angle of deviation is minimum. Then we can also prove that the angle of incidence. Now look at this. If the whole of this is I, this is a straight line and that straight line. From here to here will also be I. So since one is already R, the remaining part is going to be I minus R. The length from here to here and this are equal. So if this I minus R, this is also I minus R. I minus R, I minus R. And this D is exterior angle to this triangle. So from there we can show that D equals to I minus R plus I minus R twice. That's 2I minus R. From there our aim is to get the value of I. We can expand and say D equals to 2I minus 2R. And from here, 2R is A. 2R is A. We can replace this 2R with A. So from there it means D equals to 2I minus A. Which implies that 2I equals to what? A plus D. To get the value of I, let's divide both sides by 2. From there we get I to be equals to what? A plus D over 2. Remember, refractive index is sine I over what? Sine R in general. And here we are going to have a new formula by replacing I in terms of what? Angle of minimum deviation. What is I from here? So this is sine. What is I? A plus D over 2. A plus D over 2. Over sine. What is R? A over 2. So this is another formula for refractive index in terms of angle of minimum deviation and the reflective what? Sorry, the reflective angle of the prism. So before today's class we have 5 formulas, 5 or 6 formulas for refractive index. So 6, this makes what? The 7th one. So but this one is peculiar to, you know. But note, if this D is not angle of minimum deviation, this formula may not work for some cases. But just note this. This R, this I. So that's for what? And note, our assumption here is that this light, this particular light is monochromatic. It has a single wavelength. Then what if you have a light that doesn't have what? One wavelength? Then there will be dispersion. We are coming to that later. In summary, if you have light that falls on the prism this way, note this way is going to stop and it will refract. It will refract and touch here. After here, it will refract again out. So this is the angle of minimum deviation in this case. So this is D. And this is A. So refractive index sine A plus D over 2 complete diagram. normal. Incident ray, refracted ray, another normal, then emergent ray. Angle of incidence, angle of refraction, angle of emergence. Reflecting prisms. Ordinarily, for prisms, when light falls on them, at the end of the day, the light is meant to what? Refract through. But it is possible that instead of refraction to occur, reflection can occur, and also occur total internal reflection, which can also happen in prisms. For example, suppose we have a right angle isosceles triangle, meaning 90, 45, 45. If light falls on it, please note this. When light falls on a surface perpendicular to the surface, the number coincide with this. That light will pass through undeviated, or let's say it will refract through undeviated. Ordinarily, after refraction, the direction is meant to change, but because it enters normally to it, so this is surface, this is normal to the surface. If light enters this way, at the end it will bend towards the normal. But if the light enters normally, meaning at 90 degrees to it, to the surface, it will pass through undeviated. So when light falls on it normally, it will pass through undeviated and strike the other face. Okay, it strikes it here. Now let's draw a normal here. This angle is angle of, for this particular second face, this ray is like our incidence ray. So this is like angle of incidence. And if we are to measure this angle, or if you are to calculate this angle, the angle will be exactly 45 degrees. And we can show that by geometry. Let's show that this angle I is 45 degrees. This is a straight line. This is a normal. So meaning this angle here is 90 degrees. So therefore, this angle is also 90. Let's go on. This line and this line, they are parallel. So if this angle is 45, this angle is also 45. Because they are corresponding. So 45, 45. This angle will be 90. Now if this angle is 90, angle is 45. 45 plus 90 plus I must be 180. If you use the triangle, you get this height of 45 degrees. So when this light enters and touches this face, this angle here is what? 45 degrees. And we know the refractive index of what? Of glass. So if we know refractive index, remember, refractive index is also 1 over sine C, where C is the critical angle. So if we put the value of refractive index of glass here, and make C the subject, we are going to get the critical angle to be approximately 42 degrees. So the critical angle for a glass prism, meaning the angle of incidence, when the angle of refraction is 90 degrees, for a triangular prism, or for a triangle, for a glass rather, is 42 degrees. Now in this case, the angle of incidence in this case is 45, which is more than what? Critical angle. When angle of incidence is more than critical angle, what happens? Reflection will occur instead of refraction. This light upwards go out, but instead of going out from here, it will reflect, and this is going to reflect. Why? Why is it going to reflect this way? Because when during reflection, angle of incidence must equal to the angle of reflection. If this angle is 45, this one must 45. And if I measure from here, this line is going to be perpendicular to this. So on this face here, on this face, we have a reflection occurring instead of refraction. So the light will not go out. So this face is acting as a what? As a mirror. And for every mirror, we can capture the image of an object on it. So just note, for a glass prism, when ray enters this way, it must what? Reflect from this space here, the hypotenuse. Let us consider this arrangement. Let's consider this. Suppose we have an object here. Let's take two rays. Let me break down a bit. So one ray will come this way, enters this way. When it gets here, what happens? Same thing we have here. Incident ray, in this case, reflected ray. So this face acting as a what? Reflector. Let's take it from here also. Incident ray, reflected ray. Now for this face now, it also enter normally here. So when I get here, same thing goes for this. So at the end of the day, let's follow. This head here goes this way, down here, back here. And this tail goes here, come back here. This arrangement is a periscope, meaning we can see over a barrier. Instead of using plane mirror, remember, during under reflection, we talk about periscopes. But in that case, we use two plane mirrors. They are parallel to each other, and they are both inclined at angle what? 45 degrees each. 45 degrees, 45 degrees each. And we can capture the image of an object over a barrier. But for mirror, due to multiple reflection, the image form will be blurry because you form multiple images on top of each other and they will shift a bit. So the image will be blurry. So in a case where we want to get a sharp image and to avoid this blurry image by a periscope, the best is to use what we call prisms. We use prisms for this case. So if you have an object here, someone here will see it. Be a simple periscope. Apart from periscope, we also have what we call prism binoculars. Prism binoculars. They are like a kind of telescopes to view distant objects. Let's suppose we want to view a particular object that is very far from you. Let's suppose a tree is about 1 kilometer away from you, and there is no barrier blocking you guys. And you want to view maybe something from the tree. So we use what we call what? We can use a binoculars. Prism binoculars. What we use normally are telescopes. We are coming there under optical instruments. We talk about the microscope, telescopes, and prism binoculars. So there's a way we can set up what prism binoculars, but in that case you need to use other lenses. We are coming to lens. So in order to capture the image of an object that is very far. So in that case, there's a way we arrange it. So suppose the right angle triangular prism is made to stand this way. If the ray enters like this, if it enters this way, when it gets here, it will reflect. When it gets here also, it will reflect down. So if there's an object here of, let's say this is an object, so what happens, we can take another ray. When it gets here, it will reflect, and from here it will come back. So anything we have here, although we are seeing the same point here, so we can put another prism down here. I will continue the process. This will hit here and go out this way. Same goes for this. So an object here can be seen here. When we get to, but you still need lenses. You need to use eyepiece and what? Objective lens. When we get to optical instrument, talk about it. But the thing is, we should know that prisms can also what? Reflect light. And in that case, they have many application, many uses, which we've mentioned periscope and prism binoculars. Now let's now move to diachromatic or polychromatic light. When you have light that has multiple spectrum in it, what will happen when they fall on prisms? The concept of what? Dispersion of light. Here was a great scientist called Isaac Newton. He noticed that when white light falls on a prism, spectra are formed, or let's say spectrum are formed. For example, suppose this is a triangular prism. When white light falls on it, what happens? We add something like this. And if they are cut on a screen, we notice that we have what we call spectrum. We call them impure spectrum. The uppermost here looks reddish, while this place is a bit violet. But this is what we call impure spectrum. Then it got another prism. So this is what it did this time around. When this one gets here, it is fast. And when it came out, so it put another prism somewhere here, inverted. So when it gets here, white light gets here, it disperses into spectrum. And when the spectrum gets here, they recombine to form white light. So that's when it's discovered that, oh, it means this light has components which were called the spectrum. And they can recombine to form the white light back. So from here, it is observed that white light contains all electromagnetic spectrum. And when the distance between them is widening, using what we call converging lenses before and after dispersion, we form what we call pure spectrum. Pure spectrum are formed when we have what? Two converging lenses, one before and one after the prism. So we need a source of light that will produce what, a state of light. When they get here, there will be dispersion, and this second one will further, separate them into what we call pure spectrum. The uppermost is obviously red, orange, yellow, green, blue, indigo, and violet. That's what it is. So a pure spectrum is formed, pure spectrum are formed or is formed when we have what? Two converging lenses, or when we have a triangular prism in between two converging lenses. We need a slit of light, and we need a white screen. So this is how we form what? Pure spectrum. So the process where white light splits into its components is called what? Dispersion of light. And this is mainly due to, that's the main point to note, it is due to the fact that the electromagnetic spectrum, they move at different speed. Like red spectrum, or let me call it red light, has the highest speed, while what? Violet has the least speed. Ordinarily, since they are all part of electromagnetic spectrum, and light travel with the speed of light, or all electromagnetic waves travel with the speed of light. In a vacuum, all this spectrum, they travel with what? Speed of light. But in glass prism, inside the glass, when they get inside the glass prism, they travel at different what? Speed. And they have different what? Wavelength. So during this process, the only thing that is constant is their frequency. But they travel at different speed, and they all have different what? Wavelengths. So for every spectrum, we can assign a particular wavelength to them. These are called what? Dispersion. Dispersion can also occur in nature. For example, sometimes after rainfall, when you look at the sky, when the sun just comes out, we notice that you see what we call rainbow. A rainbow on the sky. And that rainbow is an example of impure spectrum. And it is from when after rainfall or in the cloud, when you have rain droplets, or in the cloud, they are like a spherical surface, and it also refracts light. So dispersion is a special case of refraction. So light from the sun is like a white light. It has many components. When they fall inside the bubble, they will disperse. So dispersion is due to what? Differential what? Speed of the spectrum in what? In glass or in water droplets. So that is why they refract at different angle because of their speed. They refract. Dispersion is as a result of what? Refraction in different angles due to the fact that the spectrum travels at different speed in the glass. So in pure spectrum, To get pure spectrum, we need two converging lens, triangular prism, street of light, and what? Widescreen. Now, this electromagnetic spectrum or this light spectrum, they are categorized in different ways. There are some of this spectrum that they can be formed by mixing others. For example, there's a way we can get yellow when we mix two other spectrum or light, color of light. But there are some that we cannot mix any color to. There is no combination that can give rise to them. So we call them the primary colors of light. And the primary colors of light are three. Let's start with that. Note: red has the highest speed, while violet has the least speed. As you go, it changes. In case they can form a question using this, they can give you orange, blue, and yellow. And I ask which of them has the least speed. Which one has the least speed? The answer is what? Blue. Which of these three has the highest speed? Orange. There are three primary colors of lights. Please note, when you say primary colors of light is important because we also have primary colors of paint. So for lights, we have red, we have green, and we have blue. These three lights are monochromatic, meaning they have no component within them. Red, blue, green. They are called what? Primary colors. Then we have what called secondary colors of lights. But before that, note, if we add all the primary colors in the same proportion, 1:1:1, one red, one green, one blue, will give us what? White. Very important. Secondary colors are gotten when two primary colors are mixed in the same proportion. Red plus green. We have what? Green and blue. Blue plus red. When we mix red and green in right portion, we get yellow. When we mix green and blue, we get what? Yes. And when we mix blue and red, we get what? Magenta. Magenta, very close to purple, but it's not purple. So to remember this, you can use this acronym. Red guy, go buy Coke, bring remaining money. Red guy, go buy Coke, bring remaining money. So red guy is red plus green gives yellow. Go buy Coke. Green plus blue gives what? Cyan. Blue, red gives what? Magenta. Red guy, go buy Coke, bring remaining money, or brought the remaining money. Here, don't worry about the grammar. Neglect the grammatical error. The most important thing is for you to remember this. Then we have what we call complementary colors. Complementary colors. So when we mix two secondary colors and we are getting white, they are called complementary. Red, green, blue are white, but we cannot call it complementary. Before they can be complementary, we need just two colors. So any two colors you mix to get what? White are called complementary. Now look at this. Look at this. Yellow has red and green. It doesn't have blue. So if you add blue to yellow, it becomes white. So yellow plus blue gives white. Cyan has green, blue, doesn't have red. If you add red to cyan, cyan plus red will also give us what? White. Magenta has blue and red in it. Magenta has what? Blue and red, it has no green. If you add green to magenta, we also get what? White. So yellow plus blue, or yellow and blue, cyan and red, magenta and green, they are called what? Complementary colors. every other colors we have apart from this are called tertiary. Because we can mix yellow and cyan together. We can mix yellow and magenta. In fact, we can mix yellow and red. You know, we have red and green. 1:1. If you have two red, 1 green, the yellow will be close to being red. So that's like a reddish yellow. We give it a name. So when red is a bit yellow, we get what? Reddish yellow. What's reddish yellow? Which color is very close to reddish yellow? Now let me ask a question. Is it possible light falls on a particular object and that object appears black? Yes. Let's suppose we have a particular region where there is no light at all. If you have, let's say, a green cloth, if yellow light falls on it, that green will show different color. How are we going to know? Remember, I told you earlier at the beginning of the lecture that opaque objects or objects are seen from the light they reflect. For example, let's suppose I have a particular object or a card, or let's say cardboard, and this cardboard is yellow. This cardboard is yellow. If this cardboard is yellow, it means this cardboard has two spectrum, or let's say spectra. What are what? It has red and green. So if we have a light coming, light falls on it. Suppose we have blue light falling on it. What happens is this yellow card can only reflect red and green. It will absorb every other color. So when this blue falls on it, what happens? It will absorb it, and it will emit nothing. So this appears to be what? To be black. So meaning, if we have a yellow card, like the one the referee uses in football, under blue light, it will appear black. But if we have a yellow card and a red light falls on it, what happens? It will appear red. Why? Because yellow has red and green. So what happens? It's going to what? Reflect. Or it's what? Allow the red to pass through, then absorb other. So what happens? This yellow card will appear to be red. So if you have yellow card under red light, it will appear red. Okay. Let's suppose we have a blue card, and on this blue card, a white light falls on it. What happens? It will appear blue. Why do you appear blue? Because white light has what? Red, green, and blue. When this falls on it, it's going to absorb red, it will absorb green, and it will allow what? Blue to pass through. Or it reflects blue, so you see it as what? As blue. So meaning an object will absorb other magnetic or spectrum, or other color of light. It will reflect or push back the one, like in this case, it pushes back light of its own kind. So this is what will happen. Now look at this. Another question. Suppose we have a card that is magenta in color. A magenta card, and a yellow light falls on it. What will it appear as? What will it show? Now let's check it very well. In case you don't understand the previous examples, look at this very well. First, what are the components of magenta? Blue and red. So it has blue and it has red. So it means it can only reflect blue and red. Every other color will be absorbed. Now yellow has what? In yellow it has what? Red and green. Red and green. So it means what will fall on this magenta? We have red and green. So what happens? It can only reflect red. It will absorb green. So it will appear as what? Red. So you put a magenta card which look like what? Almost like a purple. Under yellow light, it will appear to be red. So understand this very well. An object is seen from light, it what? it reflects. Okay, instead of yellow light, let's focus on this magenta now. On this magenta, instead of yellow light, we are having a green light. What will it appear as? It will appear as black, because magenta can only reflect blue and red, but what is coming here is green. It will absorb the green, and if the green light is absorbed, no light will be reflected, and if no light is reflected, it appears as black. So black means what? Absence of light. Black is not actually a color. It means there's no light at all. So if you have a region in space where light will totally be absorbed and light will not be cannot escape, that place will be what? Void black. Example, black hole. So light cannot what? Escape black hole. So when light falls on it, it will absorb it, and it always appear black. So black is not a color. It's actually what? Absence of what? Of light. So that's why this one appears what? Black. So I think we can end this version of light here, right here. Then in our next class, we will now go to lenses. What are lenses? Under mirror, we have plane mirror and curved mirror. Then under refraction also, we have plane surface where refraction occurs. We talk about rectangular prism, triangular prism. If you now have a curved glass or a curved transparent surface that allow light to pass through them, we call them what? Lenses. Lenses are categorized into two. A lens is either a converging lens or a diverging lens. For a converging lens, they converge the rays after refraction, but for diverging lens, they what? They scatter or they diverge what? Parallel rays after refraction. So, but converging lenses are made from convex surfaces, while diverging lenses are made from what? Concave surfaces. So you can say convex lenses are converging, while concave lenses are what? Diverging. Opposite to that of mirror. For converging mirror, they are concave. For diverging mirror, they are what? Convex. But converging lens and converging mirror, they are identical in property. Diverging lens and diverging mirror, they are also identical. Just that what it takes a converging lens to be concave, a converging mirror is going to be what? To be convex. A converging mirror is what? Concave. Now this converging lens can be of three kinds. We have the biconvex, planoconvex, and convex-convex, or we call it what? Converging meniscus. So this is what? Biconvex. This is convex, convex, biconvex. So when light parallel rays comes, after they what? They converge. This plano-convex, and this is what? Converging meniscus. So converging lenses, by touching them, we can identify lens either it's converging or diverging. When you check the top and the bottom, they must be tiny at the top and bottom, and the side will be thicker. The top and bottom is tiny, is thin, while the sides are what? Thicker than the top and bottom. Same goes for diverging lens. For diverging lens, you have three kinds. We have biconcave, planoconcave, and diverging meniscus. And these are diverging lenses. Biconcave, planoconcave, this diverging meniscus. So for diverging lens, if you hold the center should be tiny, while the top and bottom should be thicker. They have thick top and bottom, tiny what? Center. But for this class, we're focusing on plano convex and plano concave. So let's start with what? Plano convex. The center of lenses is called optical center, O. Unlike a mirror, for a mirror, the center is called a pole, P. Here the center, you call it the optical center. The straight line, an horizontal line that passes through this center, is called what? Principal axis, similar to that of a mirror. So this is the principal axis. Now, where is the front, where is the back? For a lens, the front can be the back and the back can be the front. Why? For this one, this is the front. For this one, this is the front. So where the object is placed is the front. Where the object is placed is the front, or where the light ray is coming from is the front. Note that. Suppose we have parallel rays coming this way. One coming this way, another one coming this way. So we'll call it the front of the lens, and this is what? The back of the lens. When these rays pass through this lens, they'll converge at a point. Where they converge is called what? The focal point, similar to the principal focus we have for a lens, for a mirror. So we can call it principal focus. So for this particular lens, if we are to draw out the sphere, it is formed from the center of that sphere, similar to center of curvature here for mirror. So this is center where this space is cut from. So this is the center of curvature. But in lens we don't use C. We call it what? 2F. If we have it at the back, we also have it at the front too. So here is F, this is also F, and this is 2F. The one at the back, we use this symbol to differentiate. This is the back, this is the front. Where you have the rays coming from is the back, is the front, while this is the back. So depending on where you place the object, we will get different images. Depending on where we place the object, we get different images. If you place the object beyond 2F, at 2F, between 2F and F, on F, and between F and O, we'll get different images similar to that of what? Converging mirror or a concave mirror. And what are the? We have what? Rays. So we have reed, yes, diminished, rays, rim, infinity. We have what? Vem. Same property. Let's try to draw two out of this. Let's draw two out of it. Let's draw when we are going to have reed and rim. Let's draw these two. That is, let's try to draw everything very quick. The first one is to know that rays, parallel rays, or when we have rays that are parallel and close to the principal axis, they converge at the what? Focal point after refraction. So if you have an object placed at infinity, meaning objects very far from the lens, the image will form at the what? Principal focus or focal point. And it's going to be what? Read. Let's try to draw a diagram to show this one. Alright, first, if the object is placed here, what will be the characteristics of the image? That's the first one. If it is placed here on 2F, what will be the characteristics? If it's placed between 2F and F, what will be the characteristics? On F, what will be the characteristics? And between F and the optical center, what will be the characteristics? The first you have to realize is any ray parallel to the principal axis passes through the principal focus after refraction. And any ray that passes through the principal focus is refracted parallel to the principal axis. Then lastly, any ray that passes through the optical center is refracted undeviated. So if the ray comes this way, it will go pass through without being deviated. So following that, let's start from this. A ray parallel to this one, after refraction passes through what? Through F. Secondly, we can use the one through F, and it's what? Any ray that passes through F, after refraction, we have something like this. So they will meet here. No, this is not horizontal enough. They will meet here. It is formed between 2F and F. So it is formed at the back. I told you where the object is placed is the front, so it's formed at the back. If it's at the back, it is what? Sorry. Oh, we have to reverse that case. What I said initially is wrong. Where you place the object is the back, rather. So this is the back. And this is the front. Because the object will be, after the observer will be here, the object will be here. Where the observer is the front, rather. So where the object is, or where the ray is coming from, is the back. You know, when you wear glasses, behind the glasses, that's where you place the object, you know. So the front, where the object is placed is the back, this is the front. So now, the image is from at the front, so it is real. Below center of curvature inverted. Now when you check the height of this, compared to this one is shorter, then it is what? Diminished. That's real. For this, we get a ray parallel to the principal axis. After refraction passes through what? F. Second one, any ray that passes through this F, after reflection it what? Pass through the principal axis, they meet here. It is formed as 2F. It is from at the front, so it is real. Below principal axis, it is inverted. And if you check the size of this and this, if you have to measure it, it will be same size. That is wrist. Similar to that of mirror. The next one, between 2F and F, ray parallel to principal axis, pass through principal focus after reflection. Then next, ray that pass through this F. After reflection, what? Refraction. After refraction, it should be parallel to the principal axis. At the end, we have this. It is from behind F. In front of mirror, real. Below center of curvature, below principal axis, it is inverted. Now it's bigger, magnified. That's ring. For the next one at F, ray parallel to this one. After refraction, passes through F. Now the second ray cannot pass through F, so we now use the center. Any ray that passes through the center is refracted undeviated. As you can see, these two rays are parallel to each other. Since they are parallel, the image will be formed at where? At infinity. Same pattern. Now, the last one, when the object is placed between F and the optical center, what will be its characteristics? We know it's going to be virtual, erect, and magnified from our knowledge in mirror. Same way, ray parallel to the principal axis, after refraction passes through F. Then ray that passes through F, this time I cannot come here, so we use the center. Ray through the center will be refracted undeviated. As you can see, these two rays are moving away from each other, so they are diverging. So they will never meet at this point, they will meet backwards. So we use extrapolated rays to join them together. So these rays are unreal. So we form our image here. So the image is formed at the back. At the back means it is virtual. It cannot be caught on the screen. It is virtual. Then above center of what? Above principal axis, it is what? Erect. Now if you check the size, this is the object, this is the image. It is what? Magnified. Verb. Same thing. So the images formed by a converging lens or a convex lens are always real and inverted, real and inverted, real and inverted, except when the object is placed between the principal focus and the optical center, where the image is what? Virtual and erect. Then as the object moves closer to the lens, it gets bigger. This one is small, diminished. Then same size, magnified further. This one is special, or is a special case, infinity. So these are the ray diagrams for that. So converging lens. For a diverging lens, similar to a diverging mirror, or for a concave lens, similar to a convex mirror, the image form will always be virtual, erect, and diminished. Vert. Let's show that here. So let's use a plano concave. Let's see this optical center. Then we have the principal axis through it. Optical center, F, 2F, F bar, 2A bar. Before we draw the ray diagram for this, the same way we show for this one, for a converging lens, when rays are coming from infinity. Let's show the same thing for the diverging lens when the rays are coming from infinity. So let these two disappear. One. When we have rays that are parallel and close to the principal axis, they will refract actually. So what happens here, when this ray gets here, it will refract. But how? It's going to refract this way. This one also refract this way. So unlike this one that converge after refraction, these two they diverge after what? Refraction. What is principal focus? Principal focus is a point on a principal axis where rays converge or diverge after refraction in this case. This one is converge after refraction. This one is diverge after refraction. So the question is, where is the focal point for this or principal focus? We throw this one back. So the divergence started from what? From F. But look at this. For a converging lens, the principal focus is where? At the front. Then the focal length, which is the distance between F and O, is going to be positive. Positive focal length. But for this one, his own focal point is at the back. So the principal focus, the focal length F is at the back, so it's going to be negative. So note, the principal focus, the focal length for a diverging lens is what? Minus, is negative. While for a converging lens is positive. Same thing. For a converging mirror, F is positive, diverging mirror, F is negative. So this is what? Principal focus for A. Now look at this, in case you ask, defined principal focus as applied to a diverging mirror. Diverging mirror, if it's mirror, you say, it is a point where parallel rays diverge after reflection. But if they now ask you, what is principal focus for a diverging lens? You say it's a point on a principal axis where rays diverge after refraction. For mirror, you say reflection. For lens, you say what? Refraction. Mirrors reflect, lens what? Refract. So no matter where you place your object, whether it's beyond 2F, on 2F, between 2F and F, on F, between F and O, the image form will always be what? Virtual, erect, and diminished. Meaning it's going to be formed at the back. At the back, this is the back, this is the front. Note. Where the ray is coming in the front, if you form it at the back, it will be erect and it will be smaller. So suppose this is our object here. We follow same what? Corollary. Rays parallel to the principal axis. They do what? Let me make this one longer. Rays to principal axis, parallel to principal axis. They do what? They refract through the what? Principal focus. In this case, after refraction. Then secondly, any ray that passes through F, or in this case we use the center, any ray that passes through the center, they refract undeviated. So this ray and this ray, if you observe, they are moving away from each other. If you go back, they met here. So where they met is where the image will form. So the image will form here. As you can see, the image is a draft here. It's shorter. First, it is formed at the back. This is the front. If it is formed at the back, it is what? Virtual. It is on the principal axis, so it is erect. It is smaller, it is diminished. It is what? Diminished. Then lastly, let's choose one of these ray diagram. Let's choose this one. This is the distance between, this is the object, this is the image. The distance between the objects and the image is called what? Object distance. Between, and the object rather. The distance between the image and the optical center is called what? The image distance. Distance between the principal focus and the optical center is called focal length. So we have a particular formula that connects U, V, and F together, similar to a mirror, and they are what? They are the same. They are the same. So in this case, we call it length formula. What is the formula? 1 over F equals to 1 over U plus 1 over V. This is what we call the mirror formula. For every length, we have what we call power of length. Every length has the power of length, P, is the reciprocal of what? Focal length. And the unit is what? Diopter. But note, if the unit is to be diopter, this focal length must be meter. focal length must be meter. Most times you'll be given centimeter. So first convert to meter. But if you are lazy to convert, just use P equals to what? 100 over F. If F is in centimeter, I don't want to convert. Just do what? 100 divided by F in centimeter. You get the what? The power of the length. Also recall, magnification is what? Image distance over object distance, or image height over what? Object height. The same formula we use in mirror still works here. Meaning, what connects M, F and U? Recall, we show that magnification M can be what? Expressed as B over F minus 1. In a question when they are not talking about what? The object distance. And in terms of what? U. The magnification M equals, that will be F over U minus F. That is the formula for magnification. The length formula, the power of length. And I think with this, we are done with everything under refraction. What is left is to solve more questions. Although there's something I've not mentioned. For a lens, either converging lens or diverging lens, how can we measure their focal length? How can their focal length be measured? It is very simple. We are going to use this first case. Rays from infinity, they do what? They converge at the principal focus after what? Refraction. So if you have a lens very far, we can place a lens from a particular object and let light fall on that object. Suppose we have a plastic, and on this plastic we put a cross line there. Then in front of this plastic we place a white screen. Then behind it we have what? Light, source of light. So what happens is, we'll keep moving the source of light, or if the source of light is fixed, we'll keep moving this object away and towards the light until a sharp image is formed at the screen, on the screen rather. Whenever we form a sharp image on the screen, it means the image is formed at the what? Principal focus. Then distance between these objects, or the image from rather, distance between the image, that's the screen, and the lens itself becomes the focal length.